Relational algebra, first described by E.F.Codd while at IBM, is a family of algebra with a well-founded semantics used for modeling the data stored in relational databases and defining queries on it. The main application of relational algebra is providing a theoretical foundation for relational databases, particularly query languages for such databases, chief among which is SQL. Introduction. Relational algebra received little attention outside of pure mathematics until the publication of E.F.Codd's relational model of data in 1970. Codd proposed such an algebra as a basis for database query languages. 5 primitive operators of Codd's algebra are the selection, the projection, the Cartesian product, the set union, and the set difference. Set operators. The relational algebra uses set union, set difference, and Cartesian product from set theory, but adds additional constraints to these operators. For set union and set difference, the two relations involved must be union compatible, that is, the two relations must have the same set of attributes. Because set intersection can be defined in terms of set difference, the two relations involved in set intersection must also be union compatible. For the Cartesian product to be defined, the two relations involved must have disjoint headers, that is, they must not have a common attribute name. In addition, the Cartesian product is defined differently from the one in set theory in the sense that tuples are considered to be shallow for the purposes of the operation. That is, the Cartesian product of a set of n tuples with a set of m tuples yields a set of flattened tuples. More formally, R times S is defined as follows. The cardinality of the Cartesian product is the product of the cardinalities of its factors, i.e., R times S equals R times S. Projection. A projection is a unary operation written as where is a set of attribute names. The result of such projection is defined as the set that is obtained when all tuples in R are restricted to the set. Selection. A generalized selection is a unary operation written as where is a propositional formula that consists of atoms as allowed in the normal selection and the logical operators, and this selection selects all those tuples in R for which holds. To obtain a listing of all friends or business associates in an address book, the selection might be written as the result would be a relation containing every attribute of every unique record where is friend is true or where is business contact is true. In Codd's 1970 paper, selection is called restriction. Rename. A rename is a unary operation written as where the result is identical to R except that the B attribute in all tuples is renamed to an A attribute. This is simply used to rename the attribute of a relation or the relation itself. To rename the is friend attribute to is business contact in a relation might be used joins and join-like operators. Natural join where R and S are relations. The result of the natural join is the set of all combinations of tuples in R and S that are equal on their common attribute names. For an example, consider the tables employee and department and the natural join. This can also be used to define composition of relations. For example, the composition of employee and department is their join as shown above, projected on all but the common attribute depth name. In category theory, the join is precisely the fiber product. The natural join is arguably one of the most important operators since it is the relational counterpart of logical and. Note carefully that if the same variable appears in each of two predicates that are connected by an, then that variable stands for the same thing and both appearances must always be substituted by the same value. In particular, natural join allows the combination of relations that are associated by a foreign key. For example, in the above example a foreign key probably holds from employee depth name to department depth name and then the natural join of employee and department combines all employees with their departments. Note that this works because the foreign key holds between attributes with the same name. If this is not the case, such as in the foreign key from department.manager to employee name, then we have to rename these columns before we take the natural join. Such a join is sometimes also referred to as an equijoin. More formally, the semantics of the natural join are defined as follows. Where fun is a predicate that is true for a relation RIFF, it is also true for relation S. It is usually required that R and S must have at least one common attribute, but if this constraint is omitted, and R and S have no common attributes, then the natural join becomes exactly the Cartesian product. The natural join can be simulated with Codd's primitives as follows. Assume that C1, Cm are the attribute names common to R and S. R1, Rn are the attribute names unique to R and S1, Sk are the attribute unique to S. Furthermore, assume that the attribute names x1, xm are neither in R nor in S. In a first step, we can now rename the common attribute names in S. Then we take the Cartesian product and select the tuples that are to be joined. Finally, we take a projection to get rid of the renamed attributes. Theta join and equijoin consider tables car and boat which list models of cars and boats and their respective prices. Suppose a customer wants to buy a car and a boat, but she does not want to spend more money for the boat than for the car. The theta join on the relation car price boat price produces a table with all the possible options. When using a condition where the attributes are equal, for example price, then the condition may be specified as price equals price or alternatively itself. If we want to combine tuples from two relations where the combination condition is not simply the equality of shared attributes, then it is convenient to have a more general form of join operator, which is the theta join. The theta join is a binary operator that is written as or where A and B are attribute names. Theta is a binary relational operator in the set less than, equals, greater than. V is a value constant, and R and S are relations. The result of this operation consists of all combinations of tuples in R and S that satisfy theta. The result of the theta join is defined only if the headers of S and R are disjoint, that is, do not contain a common attribute. The simulation of this operation in the fundamental operations is therefore as follows. R theta S equals sigma theta. In case the operator theta is the equality operator, then this join is also called an equijoin. Note, however, that a computer language that supports the natural join and rename operators does not need theta join as well, as this can be achieved by selection from the result of a natural join. Semi-join. The left semi-join is joining similar to the natural join and written as RS, where R and S are relations. The result of this semi-join is the set of all tuples in R for which there is a tuple in S that is equal on their common attribute names. For an example, consider the tables employee and department in their semi-join. More formally, the semantics of the semi-join can be defined as follows. RS equals T. TRSS, where fun is as in the definition of natural join. The semi-join can be simulated using the natural join as follows. If A1 and are the attribute names of R, then RS equals A1, then, since we can simulate the natural join with the basic operators, it follows that this also holds for the semi-join. Anti-join. The anti-join, written as RS where R and S are relations, is similar to the semi-join, but the result of an anti-join is only those tuples in R for which there is no tuple in S that is equal on their common attribute names. For an example, consider the tables employee and department and their anti-join. The anti-join is formally defined as follows. RS equals T. TRSS, or RS equals T. TR. There is no tuple S of S that satisfies fun, where fun is as in the definition of natural join. The anti-join can also be defined as the complement of the semi-join, as follows. Rs equals R minus Rs. Given this, the anti-join is sometimes called the anti-semi-join, and the anti-join operator is sometimes written as semi-join symbol with a bar above it, instead of division. The division is a binary operation that is written as R divided by S. The result consists of the restrictions of tuples in R to the attribute names unique to R, i.e., in the header of R but not in the header of S, for which it holds that although combinations with tuples in S are present in R. For an example, see the tables completed, DB project and the division. If DB project contains all the tasks of the database project, then the result of the division above contains exactly the students who have completed both of the tasks in the database project. More formally, the semantics of the division is defined as follows. R divided by S equals TA1, and TRSSR, where A1 is the set of attribute names unique to R and TA1 is the restriction of T to this set. It is usually required that the attribute names in the header of S are a subset of those of R, because otherwise the result of the operation will always be empty. The simulation of the division with the basic operations is as follows. We assume that A1 and are the attribute names unique to R and B1, Bm are the attribute names of S. In the first step we project R on its unique attribute names and construct all combinations with tuples in S. T equals pi A1, and times S. In the prior example, T would represent a table such that every student is combined with every given task. So Eugene, for instance, would have two rows, Eugene to database 1 and Eugene to database 2 in T. In the next step we subtract R from T relation. U equals T minus R. Note that in U we have the possible combinations that could have been in R, but weren't. So if we now take the projection on the attribute names unique to R, then we have the restrictions of the tuples in R for which not all combinations with tuples in S were present in R. V equals pi A1, and so what remains to be done is take the projection of R on its unique attribute names and subtract those in V. W equals pi A1, and minus V common extensions. In practice, the classical relational algebra described above is extended with various operations such as outer joins, aggregate functions and even transitive closure. Outer joins, whereas the result of a join consists of tuples formed by combining matching tuples in a two operands. An outer join contains those tuples and additionally some tuples formed by extending an unmatched tuple in one of the operands by fill values for each of the attributes of the other operand. Note that outer joins are not considered part of the classical relational algebra discussed so far. The operators defined in this section assume the existence of a null value, omega, which we do not define, to be used for the fill values. In practice, this corresponds to the null in SQL. In order to make subsequent selection operations on the resulting table meaningful, a semantic meaning needs to be assigned to nulls. In Codd's approach, the propositional logic used by the selection is extended to a three-valued logic. Although we allied those details in this article, three outer join operators are defined: left outer join, right outer join, and full outer join. Left outer join. The left outer join is written as RS, where R and S are relations. The result of the left outer join is the set of all combinations of tuples in R and S that are equal on their common attribute names, in addition to tuples in R that have no matching tuples in S. For an example, consider the tables employee and department and their left outer join. In the resulting relation, tuples in S which have no common values in common attribute names with tuples in R take a null value. Since there are no tuples in department with a dept name of finance or executive, omega S occur in the resulting relation where tuples in employee have a dept name of finance or executive. Let R1, R2, Rn be the attributes of the relation R and let be the singleton relation on the attributes that are unique to the relation S. Then the left outer join can be described in terms of the natural join as follows. Right outer join. The right outer join behaves almost identically to the left outer join, but the roles of the tables are switched. The right outer join of relations R and S is written as RS. The result of the right outer join is the set of all combinations of tuples in R and S that are equal on their common attribute names, in addition to tuples in S that have no matching tuples in R. For example, consider the tables employee and department and their right outer join. In the resulting relation, tuples in R which have no common values in common attribute names with tuples in S take a null value, since there are no tuples in employee with a dept name of production. Omega S occur in the name attribute of the resulting relation where tuples in dept name have tuples of production. Let S1, S2, Sn be the attributes of the relation S and let be the singleton relation on the attributes that are unique to the relation R. Then, as with the left outer join, the right outer join can be simulated using the natural join as follows. Full outer join. The outer join or full outer join in effect combines the results of the left and right outer joins. The full outer join is written as RS where R and S are relations. The result of the full outer join is the set of all combinations of tuples in R and S that are equal on their common attribute names, in addition to tuples in S that have no matching tuples in R and tuples in R that have no matching tuples in S in their common attribute names. For an example, consider the tables employee and department and their full outer join. In the resulting relation, tuples in R which have no common values in common attribute names with tuples in S take a null value. Tuples in S which have no common values in common attribute names with tuples in R also take a null value. The full outer join can be simulated using the left and right outer joins as follows. RS equals operations for domain computations. There is nothing in relational algebra introduced so far that would allow computations on the data domains. A unit price with a quantity to obtain a total price. Practical query languages have such facilities, e.g., the SQL select allows arithmetic operations to define new columns in the result. Select unit underscore price asterisk quantity as total underscore price from T, and a similar facility is provided more explicitly by tutorial D's extend keyword. In database theory, this is called extended projection. Aggregation. Furthermore, computing various functions on a column, like the summing up its elements, is also not possible using the relational algebra introduced so far. There are 5 aggregate functions that are included with most relational database systems. These operations are sum, count, average, maximum and minimum. In relational algebra, the aggregation operation over a schema is written as follows, where each aj1jk is one of the original attributes I1in. The attributes preceding the G are grouping attributes, which function like a group by clause in SQL. Then there are an arbitrary number of aggregation functions applied to individual attributes. The operation is applied to an arbitrary relation R. The grouping attributes are optional, and if they are not supplied, the aggregation functions are applied across the entire relation to which the operation is applied. Let's assume that we have a table named account with 3 columns, namely account underscore number, branch underscore name and balance. We wish to find the maximum balance of each branch. This is accomplished by branch underscore nameg max. To find the highest balance of all accounts regardless of branch, we could simply write Gmax. Transitive closure. Although relational algebra seems powerful enough for most practical purposes, there are some simple and natural operators on relations which cannot be expressed by relational algebra. One of them is the transitive closure of a binary relation. Given a domain D, let binary relation R be a subset of D times D. The transitive closure R plus of R is the smallest subset of D times D containing R which satisfies the following condition. There is no relational algebra expression E taking R as a variable argument which produces R plus. This can be proved using the fact that, given a relational expression E for which it is claimed that E equals R+, where R is a variable, we can always find an instance R of R such that ER+. SQL, however, officially supports such fixed-point queries since 1999, and it had vendor-specific extensions in this direction well before that.